Hello, in this video we are going to demonstrate a nice property about parallelograms. Given a parallelogram and a non-intersecting straight line, both in the same plane, the property is that the sum of the distances from two opposite vertices of the parallelogram to the straight line is equal to the sum of the distances from the other two opposite vertices of the parallelogram to the same line. In the figure shown, the distances from the consecutive vertices A, B, C, and D of the parallelogram ABCD to the straight line L are respectively A, B, C, and D. Then the property says that A plus C is equal to B plus D. We are going to present two methods to demonstrate this property. Let's see the first method. We have to consider the information that the quadrilateral ABCD is a parallelogram. One way of doing it is to state that the segments AB and CD are parallel and have the same length. Now, how to consider that A, B, C, and D are distances to the same line? We can do that indicating that the straight lines A, A prime, B, B prime, C, C prime, and D, D prime are parallel. We don't know the measure of angle AB prime. Let's say it is theta. Because the lines CD and CC prime are parallel to the lines AB and BB prime respectively, the measure of angle DCC prime should be equal to the measure of angle ABB prime. Then the measure of angle DCC prime is also theta. We notice that the segment AB and the angle ABB prime are congruent to the segment CD and the angle DCC prime respectively. Then we can take advantage of that, forming congruent triangles. We can do that drawing the perpendicular AQ from A to BB prime and the perpendicular DT from D to CC prime. Remembering that in any triangle the sum of the measures of interior angles is 180 degrees, we should notice that in triangle AQB the measure of angle BAQ is 90 degrees minus theta, and in triangle DTC the measure of angle CDT is also 90 degrees minus theta. Seeing the 90-degree angles at points A prime, B prime, and Q, we realize that the quadrilateral AQB prime A prime is a rectangle. Then QB prime is equal to A prime, which is A. We know that the length of segment BB prime is B. Then BQ should be B minus A. Similarly, we notice that the quadrilateral D prime DTC prime is a rectangle. Then TC prime is equal to DD prime, which is D. Because the length of segment CC prime is C, CT should be the difference C minus D. Now focus on triangles AQB and DTC. Sides AB and CD have the same length, and the interior angles adjacent to the side AB in triangle AQB have the same measure as the interior angles adjacent to the side CD in triangle DTC. Then, based on the case angle-side angle of congruence of triangles, we realize that both triangles are congruent. That is, they have the same shape and the same size. Remember that in two congruent triangles, sides opposite to congruent angles have the same length. Angle BAQ is congruent to angle CDT. Then the sides BQ and CT should have the same length. Then B minus A is equal to C minus D, from which it is demonstrated that A plus C is equal to B plus D. Now, let's demonstrate the property using a second method. Another way to consider that the quadrilateral ABCD is a parallelogram is to remember that in any parallelogram, the diagonals intersect each other at their midpoints. That is why we draw the diagonals AC and BD. Then, the intersection point M is the common midpoint of the diagonals AC and BD. Another information that we have to consider from the figure is that the segments AA', BB', CC', and DD' are parallel. Because AA' and CC' are parallel, the quadrilateral AA', C', is a trapezoid. Similarly, because the segments BB' and DD' are parallel, the quadrilateral BB', D', is also a trapezoid. Let's remember some properties about trapezoids. In a trapezoid, there are two sides that are parallel. They are called bases. The other two sides are commonly non-parallel and are called lateral sides or legs of the trapezoid. The segment that connects the midpoints of the lateral sides is called the midsegment of the trapezoid. Two important properties about the midsegment are that it is always parallel to the bases and its length is half the sum of lengths of the bases. Based on the midsegment property, we can deduce that the straight line that contains the midpoint of a lateral side and is parallel to the bases necessarily intersects the other lateral side at its midpoint. Then Cn is equal to Nd. The segment Mn is the midsegment and its length y is equal to m plus n divided by 2. Whenever we have a trapezoid in a problem, if the midpoint of a lateral side is also contained in another segment that is part of the problem, it is commonly convenient to draw the midsegment to take advantage of its properties. Let's go back to the problem. We see that the quadrilateral A', C', is a trapezoid because the segment AA' is parallel to the segment CC' due to the 90-degree angles at points A' and C'. The midpoint of its lateral side AC is also contained in other segment BD, which is also now part of the problem. That is why we draw the segment MN parallel to the bases AA' and CC'. We don't know its length. Let's say it is y. Based on the midsegment properties, we know that the segment MN is the midsegment of the trapezoid AA', C', Then y is equal to a plus c divided by 2. Something similar happens in the trapezoid BB', D', BM is equal to MD, and the segment MN is parallel to the bases BB' and DD'. Then the segment MN is the midsegment of the trapezoid and its length y is equal to b plus d divided by 2. From the two relations obtained to calculate y, we can say that a plus c divided by 2 is equal to b plus d divided by 2, from which we see that a plus c is equal to b plus d. Great, we have demonstrated the property using two methods. Which one do you prefer? Based on what we have done in this video, you could demonstrate a property about the distances when the straight line intersects two sides of the parallelogram. We're going to leave that as a simple homework for you. Let's solve a simple example of the property we have demonstrated. The problem statement indicates that we have to calculate x, being the quadrilateral ABCD a parallelogram. From the figure shown, we obtain the information that the straight line L is not intersecting the parallelogram, and that the segments AA', BB', CC', and DD' are perpendicular to the straight line. Then we can use the property. The relation between the unknown x and the values given is x plus 3 is equal to 2 plus 6. from which we get that x is equal to 5. Two additional notes about the property. The property we have demonstrated considers perpendicular segments from the vertices of the parallelogram to a non-intersecting straight line. But the property can be applied even if the segments are not perpendicular to the straight line. The segments only need to be parallel. That is, they only need to be contained in parallel straight lines. The demonstration of the property for this case can be done using any of the two methods we have shown in this video. In the figure, if the quadrilateral ABCD is a parallelogram and the segments A, A', B, B', C, C', and D, D' are parallel as shown by the equal measure angles at A', B', C', and D', then the relation between the lengths A, B, C, and D is A plus C is equal to B plus D. You should know that we can also apply this property in a three-dimensional space. To apply the property, we should have a parallelogram and a non-intersecting plane. The property relates the lengths of parallel segments that have each one endpoint at the vertex of the parallelogram and the other endpoint at the plane. Given a parallelogram and a non-intersecting plane, there is an infinite number of sets of these parallel segments. In the figure, we show the segments A, A', B, B', C, C', and D, D', which form a possible set of parallel segments. If their lengths are A, B, C, and D respectively, then the property is that A plus C is equal to B plus D. To demonstrate this relation, one can use any of the methods we have presented in this video. Another possible set of these parallel segments is the one formed by the segments that are perpendicular to the plane. Then the property here is also that A plus C is equal to B plus D. Whenever we are at a place where there is something built by humans, there is high probability that we will see rectangular shapes. For instance, in the image shown, we can see a relatively large number of things whose shape can be represented by a rectangle. In some places, you could also find arrays of photovoltaic panels, which are used to harness solar energy and generate electricity. Most of these arrays have a rectangular shape. When photovoltaic arrays are installed, the final position commonly results in two sides of the array being parallel to a horizontal surface. But let's imagine a situation in which a group of installers has a photovoltaic array in a position in which the array doesn't have sides parallel to a horizontal surface. And for some reason, they need to know the distances from the corners of the array to a horizontal surface. If three distances have already been measured, let's say the distances A, C, and D, you know now that the fourth distance doesn't need to be measured, because it can be calculated using the property we have shown in this video. That is, x could be calculated just using the formula x plus d is equal to a plus c. Remember that a rectangle is a type of parallelogram. Then all the properties in parallelograms can be used in rectangles. Knowing properties about geometric figures could help us solve real-life problems, because they are representations of shapes of objects that we could find in real life. For solutions to other problems in pre-university or university topics, visit 4duni.com. Thank you for watching this video. Until next time.